Yes, so we've had a break for a couple of weeks while there was the workshop and the mini symposium. And so I'd originally planned to have a kind of discussion session today about what people had found interesting in the workshop and the mini symposium, and what sort of topics you would like to cover in the rest of this course. We'll still do a little bit of that if we have time. But for those of you who are at the companion graduate course that Mira teaches yesterday, there was a lot of that happened there anyway. And for another reason, that the last lecture I sort of got halfway through a topic I wanted to cover. So I think I should first finish that topic, and then if there's time towards the end of this lecture. So there may be times you might think about what you would like to see in this course going forward. Because in the next few lectures, I will finish the sort of core main focus and then start into the sort of more topic-driven part of the course. But for now, let's continue with where we were at the end of the last lecture, whenever that was. And so we had shown that we were talking about global rigidity in two-dimensional space for generic frameworks. We had shown that globally rigid frameworks are redundantly rigid and they're free connected. And we were looking at the converse. When is a redundantly rigid and free connected graph globally rigid? Our aim is to show that all such graphs are. We showed that all graphs generated from K4 by the one extension operation and from edge additions are globally rigid. And so now we were looking at the combinatorics, and we were focusing on the special case where the graph is an R2 circuit. So briefly, that's a graph G equals VE, whose number of edges is equal to twice the number of vertices minus 2, and the number of edges induced by any subset is at most 2x minus 3 for all subsets, proper subsets X of the vertex set with at least 2 elements. Okay, and so what we did last time was
Tony,
Hi.
Is there any dimension restriction?
Oh, so this is an R2 circuit, so this is a two-dimensional thing, yes.
Oh, okay, thanks.
So if you remember back to when we were showing globally rigid implied redundantly rigid, we could do that in D dimensions. And so the redundant rigidity was in D dimensions, and we showed the D+1 connectivity, but now we're thinking only about 2 dimensions. And so we've restricted down to redundant rigidity of circuits in 2 dimensions and to D+1, so free connectivity. And so this 2 really corresponds to the dimension. So the 2 that's there and there is really the dimension we're living in as well. It just happens that count is what happens. So what we showed last time was a number of preliminary lemmas that built up some structural information about circuits, about R2 circuits, these particular class of graphs here. And we're going to continue that to try and find an admissible node whenever the graph is a free connected circuit. And so just to remind you, node is my shorthand for vertex of degree 3. By admissible, I mean we start with a circuit, we pick a node, we can do a 1 reduction, so we pick our vertex of degree 3, say V, and we delete V and its free incident edges and add an edge among the neighbors. But admissible means one of the 3 possible reductions gives you another circuit, so we can do a 1 reduction. The 1 reductions that can be problematic, and the way they go wrong in terms of not preserving the circuit property is when there exist critical sets. So that's a subset of the vertex set with 2x minus 3 edges in it. Critical sets on their own are not necessarily problematic because there could be a critical set X living over here, and we're trying to reduce V where there's lots more stuff in the way, and so there's no real effect when you add the edge over here. But the critical set is called V critical if it actually blocks V from being admissible. So it looks like over here, it contains the 2 end vertices of the edge you add, for example. And then we talked about the version of critical sets that we're actually working with, which is called node critical, which is when you're a V critical set, but you also have this additional property that the third neighbor, this one over here, which is not in the critical set, that's not so hard to show, but if that third neighbor had degree 3, it's kind of a trivial case. And so node critical has this extra assumption that the third neighbor has degree at least 4. So this is just a very quick reminder. We went through all of that last time, but it was a while ago. So I just wanted to put these terms back in your mind, but I went fast. So do feel free to ask any questions if you like.
Sorry, you just repeat node critical again. The bit about the third vertex, please.
Yeah, sure. So we take a V critical set. So that means that it's a critical set for some pair of neighbors X and Y of V. And so it's a critical set with this condition. But if this vertex here had degree 3, then that's a particular special case that we sort of say it's a trivial case. The point being that if you imagine, say you have your vertex, I'm just drawing the same picture again, but if this vertex has degree 3 and we want to add this edge, then in the smaller graph where that edge has been added, this is xy to xy, this vertex here dropped from degree 3 to degree 2. And so it's sort of obviously not going to be a circuit because circuits have minimum degree 3. So it's a very trivial reason that the one reduction fails to preserve the circuit property. So in some sense that this is trivial in the sense that it is kind of easy to see the failure. Whereas if we have the degree at least 4 here, then this was degree at least 3. So you're less obvious there's going to be a problem, and it becomes a bit harder. And so they're the non-trivial critical sets are these node critical sets, which are critical sets for a particular vertex with degree at least 4. But the way it's set up, and this is just following the Berg and Jordan paper, is that V critical specifically refers to a vertex V, whereas node critical means you're V critical for some vertex V. Okay, so hopefully all of that is now a bit clearer.
Yes, thank you.
Yeah, and Alex has said similar in the chat as well. Okay, so here's a lemma, and actually this lemma is really the sort of result that I need to have sort of 4 boards in a room. So I don't know if we can make the technology on Zoom to have a sort of a board up here and here and here and here so that you can see the previous parts of the proof. If you could do that, then I think the proof would be much easier to follow. So I will go slowly, but if it's not so digestible at certain points, please ask. But also, it is easy. Their paper is really well written, so it is possible just to read the proof and draw your own pictures as well. So I will try to make it as clear as I can, but it may be a bit difficult. So this is the key lemma, I think, in their paper. So what does it say? You take a free connected circuit, and as far as I remember, the free connected hypothesis is to apply some of the lemmas from the last lecture. We're not explicitly going to see it in the steps I don't think, at least maybe it's once or twice, if at all. But you take a free connected circuit, and suppose it's not a wheel. So in case you don't remember, wheels had this special property where you look at all the nodes in the graph. So here it's those 5, but the subgraph induced by the nodes is a cycle. Whereas we showed last time that if you're not a wheel, then the subgraph induced by the nodes is a forest. So, and forests have nice properties that make things a bit easier to deal with. In particular, they have leaves. And we also said that, well, wheels, every vertex around the outside has degree 3. So what we can do is remove that vertex and add an edge and make a smaller wheel. So they're a sort of easy case you can deal with anyway. So suppose we're a free connected circuit that's not a wheel. Choose a degree 3 vertex, a node V, with neighbors X, Y, Z. One of the neighbors has degree at least 4, and X is a V critical set containing the other 2. So this is exactly saying that X is a node critical set, and it's node critical for the vertex V. Okay, and then we're going to suppose one of 2 hypotheses is true. So the first one is that there's a non-admissible series node, and so just to remind you, you take all the vertices of degree 3. In the subgraph induced by them, a vertex could have degree 0 or 1, it could have degree 2, or it could have degree 3. The first case is called leaf node, second case is called series, and the third case is called branching. So what we're going to do in the end proof is we're going to pick a node, but we're going to be able to choose one within the forest of nodes. So we can pick a leaf in the forest of nodes, but we can only do that for in a particular subforest of this forest of nodes, and hence when you move up from this subforest of the whole thing, it might change from being a leaf to something else. So we do have to deal with a second case. We can avoid the branching case, which we talked about last time was bad, but we have to deal with non-admissible series nodes and non-admissible leaf nodes, and that's the difference between part A and B. So in A, we suppose there's a non-admissible series node called U in V minus X minus V. So we'll see pictures of this again in a second, but there was a lemma last time that said if you have a critical set, so say we have a critical set X and it's V critical, then of course X union V is a critical set as well. It's just adding a degree 2, so that's easily see that's critical. But the lemma said that outside of any critical set, as long as there's at least 2 vertices, then there's some node. So we know we're going to be able to find, because this we start with node critical, so this guy has degree 4, so we find over here there's at least 2 vertices in this sort of blob I've drawn here. If there's a non-admissible series node U in that blob, with precisely one neighbor W in X, and that neighbor W over here in X is a node, then there will be a node critical set X dash in G that properly contains X. So the point of this is we're going to set up a sort of maximality contradiction that in the main theorem we will say, suppose X is a maximal node critical set, and use this lemma to find that there is a larger node critical set that contains the first one. And so that will give us a contradiction. But this is the conclusion for the lemma, is all this setup that I sort of tried to sketch here, but you'll see a more clear picture in a moment, tells us there must be some bigger node critical set than the one X that we started with. And it also that it properly contains X. And then part B, we do the same thing, except instead of having a series node over here, we take a non-admissible leaf node and I just give it a different name. And this time we don't care about this extra condition about the neighbors. Okay, so it's quite a mouthful of a statement to take in, but let's have a go through the proof, and maybe it'll become more and more clear as I'm working through it. So part A, so here's the picture on the right, but I take U in V minus X minus V. So remember, V is our non-admissible node, just we started with, and X is the critical set for the neighbors X and Y of V, and Z is the third neighbor with degree at least 4. U is the non-admissible series node we found outside of X union V, and let's say its neighbors are W, P, and Q. By our assumption, W is in X, and we know that U had exactly one neighbor in X, so the neighbor set of U intersect X is W, and also we assumed that W was a node. So we have all this picture on the right. We also said that U was a series node, so we know that 2 of its neighbors have degree 3 and 1 doesn't. One has degree higher than 3. So let's say that P has degree 3 and the degree of Q is at least 4. Okay, so now we have this exact picture on the right, and we want to try and find some critical set that contains X, which is node critical for some vertex and it's bigger than X, properly contains X. Okay, U is non-admissible, so we learned last time that tells us there exists a U critical set Y for the pair WP. So there's a critical set containing W and P, but not Q and not U. So this is a critical set called Y. Okay. Since GV, so now we want to start understanding properties of this set Y. So the first one is that it can't be a single edge. So a single edge is a critical set, but what would that mean? That would mean W, which is a node, P, which is a node, and U, which is a node, were contained in a triangle. So that would contradict the fact that the subgraph of nodes is a forest. So we know this edge can't be present, and hence the critical set containing W and P must have size at least 3. Okay, so this is where I want to keep the picture, but keep going with the words as well. Okay, so since it's a critical set with at least 3 elements, and critical means that Ix is 2x minus 3, we know that the subgraph induced by the 2y minus 3, I'm just used to x's. This means the subgraph induced by the critical set is a 2-connected graph. The only chance it's not two connected is if it's a single edge, but it has at least 3 elements. Since it has at least 3 elements, sorry, since it's two connected, that means that every vertex has degree at least 2 in this graph, G induced by Y. So Y contains at least 2 neighbors of W, but it does not contain U, and W is a node, so it contains these 2 vertices over here. Okay. So I guess I don't really need to say the next sentence, but that this tells us that the intersection of the set Y and the set X over here, this blob, has at least 2 elements in it. But since the intersection has at least 2 elements, we don't need to worry about the special case for the count for a single vertex compared to the 2v minus 3 count. So we can apply a lemma from last time to say that X union Y is a critical set. So if you look at X union Y here, we know it doesn't contain Q, and hence it's a larger node critical set for the vertex U than X was. So X is not a maximal node critical set. So X dash is X union Y is U critical with its 2 of its neighbors in there, and the 3rd neighbor has degree at least 4. Hence, oh, and I guess the other important point was that U had exactly 1 neighbor in X. So this vertex P was in X union Y, not in X. So X union Y is strictly bigger than X. And so since P is not in X, X dash is node critical and properly contains X. So that's proved the first part. That was the easier part of this lemma, but we used the non-admissibility of U to find a critical set here, and we used the properties that we were giving in the lemma to show the union of X and Y was a bigger node critical set. It wasn't for the same vertex V, it moved to U, but that wasn't part of the statement, so that was okay. Okay, so let's look at part B. We want to do the same.
Can we see the statement of the lemma just briefly?
Sure. I can't quite fit it all on, but maybe that's the bit you want. And maybe all the color is distracting. Let me try and get some color out the way for you. So is there something you're worried about, Alex?
No, I just wanted to read it again. That was good. Thank you.
Okay. Yes. So now we're going to start. Part B. So now instead of assuming this series node with precisely 1 neighbor, instead we're only going to assume a leaf node, and then we know nothing about how many neighbors it has in X or not. And so part of the extra difficulty in part B is going to be dealing with the various options there. Okay, so again, we have a non-admissible node V, 2 neighbors X and Y are in some critical set, a node critical set, so the degree of Z is at least 4. We have a non-admissible leaf node T. T is non-admissible, so there exist T critical sets. Make that more clearly a Y rather than a half. This is a node critical set Y2 and a node critical set Y1 for 2 of the pairs of the edges and of the neighbors, sorry. By a lemma from last time, you know, in fact, that there's always 1, 2, 3 possible critical sets that block the 3 possible reductions. So from a lemma from last time, we can always choose 2 of them, Y1 and Y2, such that Y1 union Y2 is actually all of the graph except for the critical set, that they intersect in at least 2 elements, and so that if T has a neighbor of degree 3, if T has a neighbor R which is a node, then we can choose R to be in the intersection. So that's what I've done here. So R is in the intersection of Y1 and Y2. So T was a non-admissible leaf node, so it may or may not have a neighbor which is a node. If it does, it has exactly 1, and we can choose that 1 to be in the intersection and know that these other ones have degree at least 4. Okay. So by the way, I should also, in case it wasn't clear, here y1 union y2 is everything apart from t. So while I've drawn the picture over to the right, that's because I don't know yet where y1 and y2 intersect with x and v and z. So I just drew it to the side rather than, we're now going to have to work on whether parts of y1 and y2 intersect which parts of x to try and get x union something to be a bigger node critical set. Okay. So y1 and y2 are node critical and have at least 3 elements. Okay. If x was only a single edge, then this would be an easy case because x and y are in the union y1 union y2 because y1 union y2 is v minus t. But we know that since they give us everything, we know, if this was a counting thing we did last time, that the edges between them don't exist. Okay, so xy would have to be, xy can't be like that, I'm saying, so xy would be in here or it would be in here. So it's induced by one or other of the yi. And if that's true, then since y1 or y2, whichever one it is has more than 2 elements in it, we would know that this x was size 2 and y1 or y2 would be size 3 and hence would be at least 3. So it would be a bigger node critical set. So we could just take whichever one it was and we'd be done. So we can assume x has size at least 3. We know that everything but t is in y1 and y2, and we know t is not in x. Hence these sets of size 3, at least one of them, so x has at least 3 elements, and all of them are in y1 union y2, and there's only 2 of them, so one of them has to have at least 2 of them. Okay, and now we have at least 2, we can take the union of x and y1. Okay, but first what I want to worry about is this node t, how many of its 3 neighbors lie in x? Okay. So we have a critical set x, and there's this node t. If it has 2 neighbors in x, since it's not the neighbor of v of degree at least 4, then x union t is critical, and our bigger node critical set would just be x plus t. So that was a trivial case. So we know the number of edges between t and the critical set x is at most 1. So which is basically saying that the neighbor set of t intersect x is at most 1. We just said that x intersect y1 has at least 2 elements, so x union y1 is critical. Again, this is a lemma from last time. So now we can look at this picture. So again, v, x, y, critical set x. The reason that x is node critical is z has the high degree. We know that at least 2 things in the intersection of x and y1, and t has its, if there's a low degree thing, it's in the intersection of y1 and y2, and here's our non-admissible leaf node t. Okay. So now we want we know there's at most one of the neighbors of t is in x, but we want to worry about exactly how that happens. So here's a case. Suppose the neighbor set of t intersect x is contained in y1. So we know there's some nice intersection here. Suppose that contains the neighbors. So maybe both of these or maybe one of these. Oh, sorry, at most one of these because we got this. But now the lemma would be complete because we could just take x dash to be x union y1, because if the neighbor set here is contained in y1, then this vertex, which we know has degree at least 4, is not in x union y1, and so x union y1 is node critical for t, so we'd be done. Okay, so we know there's at most one neighbor of t in x, and we can assume that the neighbor of set I guess I've gone to an equals 1 to make this, so maybe that becomes clear in a moment. But so for now, assume that the neighbor set of t intersect x is s, and s is not in y1. So s is some vertex over here that's really, this is maybe just make a big vertex s that's in y2 and in x. Okay. So we know it's not in Y1, and we were able to choose Y1 and Y2 so that the intersection contained the node if there was a node adjacent to T. So we can assume that S has degree at least 4. So the bracketed thing is what I just said. So since S is in Y2, if X intersect Y2 is greater than or equal to 2, then we can do the same thing, because this neighbor in Y1 that's not in Y2 has degree at least 4. So X union Y2 would be the desired node critical set that's bigger than X. Hence, X intersect Y2 is exactly S. So this intersection of X and Y2 is exactly this one vertex X. Okay. So I draw the picture yet one more time. Again, so here's V and X, Z, T. Y1 intersect X still has at least 2 elements, we know that, but X intersect the neighbors of T is exactly the one vertex S. Okay, so that's the size 1 thing. And then if there's a node that's a neighbor of T, it's in this intersection over here. So that's the sort of all the setup we have. Apologies if I've lost anyone. As I said, it is actually better just, I think, to read the proof and go through it step by step. But I want to at least show you the feeling of how to do these kind of arguments, because they're really nice and really important. Okay, so what we're going to say now. So since the edges from T to X union Y1 is 3, so what's that? So X union Y1 to T, so Y1 contains this vertex that's adjacent to T and this one, and X contains the other neighbor. So all 3 of the edges from T go to X union Y1. But X union Y1 is critical, so when you add a degree 3, you get the entire circuit, and so X union Y1 is all of V minus T. And we also know that X minus S must be contained in Y1, because it was also true that Y1 union Y2 is equal to V minus T. So what that tells us, if you put those 2 facts together, is that V minus Y1 is exactly this pair of vertices S and T. So it's exactly S and T if you just take Y1 away from V. Okay? I'm worrying I'm losing people, but anyway, so as I say, it's let me just finish and then maybe I'll stop for questions. So we know that the degree of S is at least 4, but this is enough to give us a contradiction and finish the proof. Why? Because we have this lemma that says if you look outside a critical set and you find there's at least 2 elements, then there exists at least 2 nodes. But we've looked outside the critical set Y1, we found there's at least 2 elements, but one of them has degree 4, so there's at most 1 node. So this contradicts one of the counting lemmas we did last time. And so this contradiction deals with the last possibility. So all the possibilities in this part B either gave us directly a bigger critical set, or we found that the option that was that we hadn't dealt with gave us a contradiction. Okay, so let's look at the statement again, and if you want to ask any questions, please do. So we took a circuit with some properties, and we particularly had a non-admissible node, and then you look outside of that vertex and the critical set that blocks admissibility for that vertex on just one of the particular reductions. We didn't need to look at all 3, just at one. So just outside this critical set X that was node critical for the vertex V. And we found, well, we said if there is a non-admissible series node with precisely one neighbor in X, or if there is a non-admissible leaf node, then we can make a bigger node critical set X dash than X. Okay. And so maybe the technical details of why that's true are not so important, but I like it and did think it's worth at least trying to convince you of why it's true. Okay, so feel free to ask, as I said, otherwise I'll move on to show you how it's used in the proof of the theorem. Okay, so as I say, that this and the last lecture are all really from just explaining this nice paper. What I've stated as a theorem is actually weaker than what they prove. So I'm stating here as a theorem is if you take a free connected circuit, it's not K4 because K4 is the smallest possible one, so it has at least 5 vertices, then you have an admissible node. What they really show is stronger than this because they do exactly what I've done so far and what I'll do in the proof, get an admissible node, and then they notice that you can make, we basically pick a leaf in a forest, but forests, as long as you have at least one edge, you also have at least 2 leaves. So you can easily get 2 admissible nodes, and then they work a bit harder to actually find either 3 pairwise non-adjacent admissible nodes or 4 non-admissible nodes. And they show that these are best possible, but I'm not so worried about how many you can find. I just want to prove the fact there is at least one, because that's what we need for our purposes. Okay, so we already talked last time about wheels and mentioned it briefly this time. So we suppose we don't have, our circuit is not a wheel, and hence take all the degree free vertices, look at the subgraph induced by them, we know it's going to be a forest. So let's define script X to be the set of all node critical sets in our graph G. So we know if a vertex, a node is non-admissible, then there is a node critical set. So if there's no node critical sets, then we're done. So we can suppose this set is non-empty, and hence we can choose a maximal element of the set. Okay, so we choose a biggest node critical set, and then we want to find a bigger node critical set and get a contradiction. Okay, so X is node critical, so there exists some node and a vertex adjacent to that node, such that X is critical for that node, and the vertex has degree at least 4 and is not in the V critical set. Since X plus V is critical and the degree of T was at least 4, we know that there are at least 2 vertices outside of X plus V. And hence we can apply a lemma from last time to say that there are at least 2 nodes outside of V minus X minus V. So now we want to look in this part of the graph V minus X minus V, and we want to look at the degree free vertices in that part. So take the subset of all degree free vertices and intersect it with this part outside and call that W. We know that there's at least 2 nodes in V minus X minus V, so W has at least 2 vertices. Okay, so I want to consider the subgraph induced by W. We know that W is at least 2, so it has at least 2 leaf nodes, so the vertices of degree 0 or 1 in GW. But since GW is a proper subset of the subgraph of nodes, the fact that these vertices are leaf nodes in W does not tell us that they're necessarily leaf nodes in G. So it could be that they are adjacent to vertices in the critical set, and hence that have degree free, and hence their degree in the subgraph of nodes in GV3 would be higher than it was in GW. So this is why we're going to use both parts of the previous lemma. So it might be that the leaf we find is a leaf in GW, is a leaf in the whole graph, and we could apply that part, or it might be that it has a neighbor in the critical set X, and hence it goes up to be, which is a node, and hence it goes up to being a series node when you move from GW to GV3. Okay, but anyway, we'll see that in a second. So every vertex in V minus X minus V minus T, maybe I should draw a picture, I guess. So we have, let's use this color. We have V, we have our critical set X, we have our neighbor T of degree at least 4, which shows it's a node, and we pick a vertex over here. So each vertex in V minus X minus V minus T has at most 1 neighbor in X, because if it has 2 neighbors in X, then X union, whatever this thing is, let's call it W temporarily, then X union W would be a critical set that's bigger than X, contradicting the choice of X as a maximal member of the set of all node critical sets, because obviously this X union W would still be node critical for V. If it had 3 neighbors in X, then you would already be have a problem, because X union W would be the entire circuit, so that would be bad as well. So we know that W has at most 1 neighbor in X, and I'm not sure if I want to use W yet for the latter, so let's get rid of that. Okay, yeah, W was a bad choice because I'd already used it here. Whatever that extra one was, I wasn't meaning it to be W necessarily, because it was for any vertex. Okay, but in particular for U and W, they cannot be branching nodes. So remember, branching node, if U was a branching node, it would have 3 neighbors in the forest of nodes, but we know it has at most 1 neighbor over here and at most 1 neighbor over here, so that would only give it 2 neighbors, which would make it into a series node. So, and if it has none over here, then it has at most 1, and it would be a leaf node. So either U and W are going to be a leaf node or a series node. But in both cases, we're basically done by the lemma before. So if U is a leaf node, then that was the only assumption needed in part B of the previous lemma. So we just apply the previous lemma to find a larger node critical set, which contradicts the maximality of X and would mean that actually U would have been admissible, and so we'd be done. And if U is a series node, then U is a leaf node in G of W, and it has precisely 1 neighbor in Y, and hence, because it's a series node, that neighbor is a node, and that means we've satisfied the assumptions in part A. And so we can again apply the previous lemma along with the maximality of X to deduce that we're going to get a contradiction, and hence find that U must be admissible. And hence in all cases, we've found an admissible node, and so we've completed the proof of the theorem. Okay, so I think I should stop for comments or questions for a minute. I could move on to the next part, and I want to say a bit more about circuits. So there is a natural continuation which might take the rest of the lecture, or we can stop. We can have questions about what I've just been presenting, or we can go back to what I said at the start and have more of a bit of a discussion about any questions you have from the mini symposium or from the workshop, or any topics that you'd be interested in hearing more about, or even topics you would like to present. If you want to give a guest lecture on something that's relevant, say. So I'm going to throw the floor open for a few minutes for comments. If there aren't sufficient comments or questions, then I will move to the next note thing in OneNote and talk a bit more about circuits for the last 10 minutes.
Hi, Tony.
I wonder if you could detail a little bit there is a very close connection to these talks to graph theory, but graph theory is such a humongous field, and what part of graph theory is your lectures and Mira's are focused on?
So I'm not sure I'm going to be so well placed to comment on Mira's lectures, because I am not attending every single one of them. But for mine, really we're doing a kind of graph theory that is not so common in sort of say structural graph theory or things about graph minors or graph colorings. we're really doing graph theory that more comes up in combinatorial optimization and sort of matroid theory. So what you've seen me present in the lectures is recursive constructions of graphs, which is really the technique or the tool that I like most in rigidity. So we always have these results to sort of say, like the Maxwell result that says if you're minimally rigid, then your graph has some count that links the number of edges to the number of vertices. So there's some constant. In Euclidean D space, it's like this, and you get a corresponding inequality. And this gives you a class of graphs to study. And what we want to study it by is understanding its properties. But we can't ever forget the rigidity. So my point is, you can't just say it's this area of graph theory, because what I want to understand this class of graphs, yes, and that's a purely graph theoretic problem, but I want to understand it with the purpose of applying it to a geometric problem. And so there are classes of graphs where that come up that people have studied in pure graph theory, but it's often the case that, or if you just study them in a purely graph theoretic sense, you might find here's a way to understand them, but I've no idea how to apply it in the geometric context. So I don't really want to suggest that the combinatorics of rigidity is some particular sub-area of graph theory. It's more its own thing, which uses some graph theory and some geometry at the same time, and you can't really separate the two. I don't know if that's
great. Great answer. And I have a similar question about combinatorics and probability, because there are a lot of people who do combinatorics in very heavy stuff, like to drop names is Erdős, the Hungarian school, Yuval Perez, and other names that you don't want me to list further, but you know what I'm asking.
So if you're asking the same question for combinatorics, then I think I can only really say my previous answer still applies, because the area of combinatorics, at least to me, that's relevant to rigidity is graph theory. So to me, graph theory is a huge part of combinatorics, but things like designs, Latin squares, counting problems, enumerative combinatorics, these kind of problems are somehow distinct from mainstream kind of rigidity problems. So they're interesting areas of mathematics, but I'm not sure they're relevant directly to rigidity. Probability is obviously a huge thing. I haven't said anything about probabilistic techniques in rigidity before. There's probably a lot of nice open problems in this area. I tentatively hope to have one lecture on sort of rigidity of random graphs. So there's various kind of, but just to give you a sort of 1 minute overview of that, there's various kind of problems you could ask. So one natural one is to say, here's a class of graphs, for example, 4 regular graphs, and you want to pick a 4 regular graph at random. So you have a bucket with every single 4 regular graph on n vertices. You want to pick one at random and ask, is it rigid in 2-dimensional space? So every 4 regular graph has this. That's just from the handshaking lemma. Whereas for a minimally rigid graph in 2D, you need to have this many edges. So you have a chance of being rigid because you have 3 spare edges. So you may even be redundantly rigid if you get lucky. And so there's a paper by Bill Jackson, and I think both Brigitte and Herman Sabatius, but definitely at least one of them, where they study this and sort of say, asymptotically, almost surely, if you pick a 4 regular graph at random, then you will be, I want to say globally rigid even, but definitely rigid generically. There's a different kind of problem where you might be interested in, say, in percolation problems in physics. And so you might go to an Erdős-Renyi random graph model. So maybe, and this I'm not very good at, so I might get this wrong, but this is sort of the way I sort of picture it. So you have all the vertices, and by all the vertices, you might have millions and millions and millions of vertices. And then you start adding edges with a certain probability. And so you want to know, with certain probability, I had an edge, so maybe I tried this one and it didn't add, that one it did, etc., etc. And at some point, there's a phase transition where you you go from having something that looks a bit like what I've shown here, where there's just the odd isolated edge, and there's a sudden sharp transition to having a giant connected component. So you suddenly have, instead of having almost nothing connected at all, you suddenly get, as the probability increases, you suddenly get some big lump in your graph. And so this is a very well studied thing in the, I think, the Erdős-Renyi random graph model. But there is a paper by, I'm going to be bad and say Lewis Ferran and co-authors, because I can't remember their names. So apologies to them, where they study the rigidity transition in random graphs. So the emergence of giant rigid components. So instead of looking for a connected graph, which would be a rigid component in one dimension, but they're looking for two-dimensional rigid component to emerge in this sort of random graph process. So I'm not a probabilistic expert at all, so I'll just mention those two basically references for if you're interested in looking at probability versions of rigidity questions.
Thank you very much.
Thanks. Alex, were you going to ask something before?
Well, you mentioned you were going to talk about circuits next, and I had been wondering for a while, just for a list of all known circuits in R3, something like that.
Oh, in R3. So I was going to, so I've been talking about circuits in 2D. I was going to keep going a bit more, but I will do that next time now, because I don't like to finish late. So we'll just keep these questions going for as long as you guys are asking them. You're interested in 3D circuits. Okay, so are you interested in three-dimensional circuits or three-dimensional flexible circuits? Or should I explain the difference?
Either one. I mean, I've just been, the idea popped into my head that even in 2D, just seeing a list of the circuits, either flexible or non-flexible, would be something I should work out, but I haven't done it yet.
So in 2D, there are no flexible circuits. Every circuit is rigid. This is a consequence of the Polychek-Geringer-Leman theorem. And testing whether, so in 2D, a circuit, as we've been talking about, is a graph that has this condition, that's one of these graphs, for all proper subsets x of v with x at least 2. And you can test these conditions by the Pebble game algorithm that I briefly described in one of the lectures. And so you can efficiently tell if a graph is one of these or isn't. So I think that there's not really much interest in listing them all out. They exist on every number of vertices from 4 upwards. And as soon as even if you get to 10, there's probably many non-isomorphic ones, but you can test if a graph is one or not easily. In 3D, it's much more interesting. So I tried to say some words about this in the three-dimensional rigidity lectures, but so they split into rigid circuits and flexible circuits. And the flexible circuits, which do not exist in 2D, are one of the major reasons why we don't understand three-dimensional rigidity. So understanding and listing these guys would be great, and I'll say something about that in a moment. These ones, they're rigid circuits, so we know that E equals 3v minus 5, and I of x is at most 3x minus 6 for all proper subsets x of v with x at least 3. But there are graphs that satisfy this that are not. This combinatorics is not enough to characterize rigid circuits, whereas in 2D it was exactly this. It's not exactly this in 3D, but we know all circuits satisfy this. And again, you can give examples for all numbers of vertices, and many of them will exist. And so again, I don't think it's probably going to be so interesting to list them, but listing these ones is interesting. So there's a paper, I'm not sure if it's been published yet or not, but there's a paper very recently by Tibor Jordan and a paper by Georg Georg Grassiger, Hakan Gula, Bill Jackson, and myself, again very recently, where we basically understand flexible circuits in D dimensions, but in very special cases. So in Tibor's paper, he looked at all graphs with at most D+4 vertices, and he showed no flexible circuits exist. Okay, if you fix dimension 3, this is only saying up to 7 vertices, so it's not very much, but D could be anything, so it's still a nice infinite class. And we looked at the same problem, but we pushed it a bit further to D+6 vertices. So again, in dimension 3, that's only talking about 9 vertices. But here on 8 vertices, so on 8 vertices in 3D, there is a unique flexible circuit. So it's this graph.
This is the double banana.
Yeah, and so we saw this in a previous lecture. So this is exactly the only flexible circuit in 3-dimensional rigidity on at most 8 vertices. So that will be the first one in your list. On 9 vertices, I forget how many there are. So you can do a 1 extension on this graph. If you do a 1 extension, but obviously when you do a 1 extension, there's probably several options for where so you subdivide some edge, say this one, by a new vertex, but then your additional 3rd and 4th one might go to here and here, or they might go to here and here. If they go across the 2 vertex separation here, then that's not a sensible thing. But there's a couple of options. And if you go above,
Hey, Tony.
Yeah.
When you do this 1 extension, is it going to be flexible for the exact same reason that it rotates about those 2 vertices?
Yeah, because I've picked the extra neighbors for these 2 edges to be on this sort of side of the thing. Yes, so it'd be exactly the same reason.
Are there any examples where it's not a hinge like that?
So on D up to D+6, no. So on D+6, and most D+6 vertices, every flexible circuit in any dimension fails to be deconnected. So there's always at least at most D-1 vertices that you can rotate around. So they always have that. Above D+6 vertices, you get much more complicated flexible circuits. So in 3D, the smallest free connected flexible circuit that I know of, and I think probably this is probably provable, but I'm not sure anyone's ever tried to write down a specific proof for it. But the smallest flexible circuit that is free connected in 3D that I'm aware of, that's definitely a true statement, is this graph. So I'm using a different color because I just want these edges to be clear. But you have this ring of K4s, and then you add, and you've drawn it to 1. So it's really a load of K5s, all the K4 red K4s plus the blue joined together, and you can get rid of some of the shared edges. And so this is a flexible circuit on 13 vertices.
Interesting. And I'm sure it's hard to picture. What is the flex? What does it look like?
Oh, I don't think I've tried to picture it. So I think
could probably do that.
If you think of it as these K5s, what's the 1, 2, 3, 4 K5s? You should think of it as like a body hinge framework, so that the K5s are sort of hinged together. And if you think about it carefully for a few minutes, I'm sure you'll be able to, or maybe you can do a nice computation quicker than that. And
yeah, that's what I was thinking. Just very dumbly compute it. But just to make sure I know the graph, these green dotted edges, those are not edges.
Correct. They are not there. Yes.
Okay.
So this blue vertex is adjacent to all the things around the outside, and exactly one of the 4 inner vertices, so that it doesn't matter which one, it would all be the same.
Okay, yeah, that was a really good answer to my question. Thank you.
And so just to finish the answer, if you go above dimension 3, then you also get the flexible circuits, which are KD plus 2D plus 2. So this is not just free connected, but can be quite highly connected. You can get quite highly connected by examples in higher dimensions.
Wait, you just wrote, do you mean bipartite, or what is this graph?
Oh, sorry. Yeah. Sorry, I don't mean the K there. I do mean exactly the complete bipartite graph, KD plus 2, comma D plus 2.
Okay, thanks.
So in 3D, K5, 5 is a circuit, but it's a rigid circuit. Whereas K6, 6 and 7, 7, etc. in the relevant dimensions are all flexible circuits.
Wouldn't the motion in that K5 example have to be like some weird wiggling at those hinges?
Yeah, so the K5s joined together at the hinges. I haven't, to be honest, I just haven't thought about it, but it will be some wiggling at the hinges, yes.
Yeah, okay.
Because I think this example was found by thinking about body hinge. This example was found, as far as I understand, by Tay in a paper in the 80s. And I think he was thinking about body hinge frameworks, and it came from that. You look at the body hinge combinatorics, and you can find this sort of picture. Okay, so it's go on.
Sorry, I just had a question. So you said for was it D less than or equal to the problem where what was it? With this example, it was the smallest. Yeah, maybe further up the problem with the double. Yeah, that inequality right there. I think it is what it was. Is there like any hope of maybe classifying 3D rigid graphs for like this? Because what was the question that Alex asked? I forget exactly what it was. When there's a graph in 3D that has a flex that isn't, I guess, around a cut. That's what it was, perhaps.
So just this paper, we studied flexible circuits when the number of vertices was close to the dimension and with this inequality. And for all such graphs, we do give a Leman theorem. And so it's basically what you're thinking and what Alex was thinking, that what we show is that all the flexible circuits have a 2-vertex separation like this. And so the Leman type theorem is basically free connected plus the count. But there's a small exception, because I think that if you're on exactly D plus 6 vertices, you can have a flexible circuit with 2 degrees of freedom rather than 1 if the dimension is at least 4. So you have to say you don't contain this particular graph as a subgraph. But you can read that precise statement in the paper, but it's roughly what you're thinking. Free connected is enough of an extra condition because the number of vertices is small.
Yeah, okay. So then
that's clearly not true if you go just to what did I say, D plus 6? So 3 plus 6 is 9. So it's not so far to get to examples where it's definitely not true, but maybe up to 12 in 3D it is true.
Yeah, so I guess that that simpler obstacle is well understood, but the harder obstacle is when that isn't sufficient, when there's some other weird stuff going on.
Yes, so what the condition is to rule out something like this, or in higher dimensions. So in dimension 4, then examples like this make me really worried about. There must be horrendously complicated flexible circuits, but in 3D, all the ones we found on this number of vertices were quite nice. And Georg has continued and has some computations for fixed dimensions, small dimensions D, where you push D plus 6 to D plus 7, D plus 8, etc. And so on small vertices above our range, it still seems to be true that it's generally nice things, or maybe the odd exception like this one that's already known. There doesn't seem to be much surprising yet.
Okay, thanks.